Let me start with a claim that sounds almost wrong the moment you hear it. Cold does not exist. Not metaphorically, not philosophically, physically. There is no substance called cold anywhere in the universe. And once you understand why, you'll never think about temperature the same way again. Think about a normal morning. You step outside and say it feels cold. You open your freezer and feel that rush of chilly air. You touch ice and instantly label it cold. It feels obvious, almost unquestionable. But physics is often at its most interesting when it challenges what feels obvious. So let's start with something familiar. Picture yourself sitting in a comfortable room, maybe around 70 degrees. There's a mug of hot coffee on the table. Leave it there long enough and it cools down to room temperature. Everyone knows that happens. But what actually occurred? Where did the heat go? The answer is simple but important. The heat moved into the surrounding air. The coffee's molecules were vibrating rapidly, carrying lots of energy. When they collided with slower-moving air molecules, some of that energy transferred outward. The coffee slowed down, the air sped up a bit, and the temperature difference shrank. Heat flowed from hot to cooler surroundings. Now, flip the situation. Place an ice cube on the same table. It warms and melts. Did the ice release cold into the room? Did the room absorb cold from the ice? Not at all. What really happened is that heat flowed from the room into the ice. Energy moved into the colder object, not cold moving outward. This difference matters. Heat is something real. It's energy that moves, transfers, and spreads. Cold is not something moving. Cold is simply what we call a region with less heat energy. Think about darkness. Darkness isn't a substance you pour into a room. You don't add darkness. You remove light. Cold works the same way. You don't add cold to make something colder. You remove heat. That might sound like a linguistic trick, but it's actually the key to understanding temperature itself. So what is temperature really? Temperature is motion. More precisely, it's the average motion of tiny particles. Every object around you is made of atoms and molecules, and those particles are constantly moving. They vibrate, rotate, collide, and drift. The faster they move on average, the higher the temperature. The slower they move, the lower the temperature. In a gas, for example, molecules zip around in all directions. They don't all travel at the same speed, but they have an average energy. That average kinetic energy, the energy of motion, is directly tied to temperature. In fact, physics gives us a precise relationship. The average kinetic energy of molecules equals 3/2 times Boltzmann's constant, times the temperature. That equation connects motion and temperature at a fundamental level. This has an extraordinary consequence. Motion can be reduced, but it can't become negative. Particles can slow down more and more, but they can't move less than not moving. That's why temperature has a lower bound. There is a coldest possible state called absolute zero, where particles have almost no motion left. It sits at about -273 degrees Celsius. You can approach that limit, but you can never quite reach it. And there's a deep reason for that, one rooted in the fundamental laws of nature. And that's where things start getting really interesting. Because when we look closely at why absolute zero is unreachable, we discover that the universe itself refuses to become perfectly still. The reason the universe refuses to become perfectly still comes from one of the deepest ideas in physics. Even if you could remove almost all motion from matter, you can never remove every last bit of it. Absolute zero can be approached, but never reached, and the reason lies in quantum mechanics. At the smallest scales, particles obey rules that feel almost paradoxical. One of those rules is Heisenberg's uncertainty principle. It says that you cannot know both the exact position and the exact momentum of a particle at the same time. If a particle had zero motion, its momentum would be known exactly, but that would force its position to become completely uncertain. Nature doesn't allow that. So even in the coldest possible state, particles retain a tiny amount of unavoidable motion. This is called zero-point energy. It's the restless hum of the universe that never goes away. That fact alone tells you something profound. The universe is never perfectly still. Even in the emptiest regions of space, even near absolute zero, there is always some motion, some vibration, some residual energy. Cold is not a substance waiting to fill space. Cold is simply the approach toward this minimal motion. Let me explain it in the simplest way possible. Imagine a box full of rubber balls bouncing around. If they bounce quickly, we call the box hot. If they bounce slowly, we call it cold. But they never completely stop bouncing. When you touch a hot object, its fast-moving particles collide with your skin and transfer energy to you. Your molecules speed up, and you feel warmth. When you touch something cold, the opposite happens. Your faster molecules collide with slower ones and give up energy. You slow down. You feel that loss of energy as cold. Nothing entered you. Energy left you. That's why touching metal feels colder than touching wood, even when both are in the same room. The metal isn't colder. It just conducts heat away from your hand much faster. Your skin loses energy quickly, so it feels colder. Wood removes heat slowly, so it feels warmer. Your body isn't sensing temperature directly. It's sensing how quickly it's losing heat. This also explains something most people misunderstand about refrigerators. When you open the door and feel cold air, it seems like the refrigerator is producing cold, but a refrigerator doesn't make cold at all. It removes heat. Inside the fridge is a fluid that evaporates at low temperatures. When it evaporates, it absorbs heat from the interior. A compressor then squeezes that gas, heating it up, and pushes it to coils on the back of the fridge where it releases the heat into your kitchen. The cycle repeats continuously. Heat is being pumped from inside the fridge to outside. That's why the back of your refrigerator feels warm. It's dumping heat into the room. In fact, the total heat released into the room is greater than the heat removed from the fridge interior because the compressor uses electrical energy, and that energy ends up as additional heat. Leave the fridge door open and you won't cool your house. You'll warm it slightly. Every cooling system in existence works this way. Air conditioners, freezers, even your own body's sweating mechanism. They don't create cold. They move heat from one place to another. There is no cold fluid flowing around, only energy being transferred. Now let's zoom in to what happens when two objects at different temperatures touch. At the boundary, billions of microscopic collisions occur every second. Faster particles from the hot object collide with slower particles from the cooler object. Each collision transfers a little energy. Over time, the difference disappears and the two objects reach the same temperature. This is thermal equilibrium. Notice the direction of the transfer. Energy flows from hot to cold on its own, every time, without exception. It never spontaneously flows the other way. This simple rule is so universal that it became one of the most important laws in all of physics, the second law of thermodynamics. And this law doesn't just describe heat. It quietly governs the direction of time itself. The second law of thermodynamics doesn't just explain heat transfer. It explains why the universe has a direction. Energy naturally spreads out. Differences in temperature fade away. Hot things cool, warm things equalize, and ordered energy gradually becomes more evenly distributed. This spreading of energy is what physicists call an increase in entropy. Entropy is often described as disorder, but a better way to think of it is the number of possible arrangements energy can take. When heat is concentrated in one place, there are relatively few ways to arrange that energy. When it spreads out, there are vastly more possibilities. Nature almost always moves toward those more probable states. That's why heat flows from hot to cold and never the other way around unless we force it with work, like in a refrigerator. This simple tendency gives time its arrow. You remember the past because entropy was lower then. You don't remember the future because entropy hasn't increased yet. Broken cups don't spontaneously reassemble. Spilled milk doesn't leap back into the glass, and your coffee doesn't heat itself up on its own. All of these would require energy to spontaneously concentrate instead of spread. The laws of probability make that unimaginably unlikely. Now here's something interesting. None of the fundamental thermodynamic laws talk about cold as a substance. They talk about energy, heat, motion, equilibrium, and entropy. Cold never appears because it isn't a physical entity. It's simply the description we give to regions with less energy. Historically, this wasn't always understood. In the 18th century, scientists believed heat was a fluid called caloric. They imagined hot objects contained more caloric, and when they touched cooler objects, the caloric flowed between them. It seemed reasonable at first. It explained why objects expanded when heated, and why warmth transferred between bodies. But cracks in the theory appeared. In the late 1700s, Count Rumford observed cannon barrels being drilled in a workshop. The boring process generated enormous heat through friction. Water poured on the barrel would boil, yet the metal never seemed to run out of this supposed caloric fluid. If heat were a substance stored in the metal, it should have been depleted eventually. Instead, the heat kept coming as long as mechanical work continued. Rumford realized heat had to be something else. It wasn't stored fluid. It was motion, the result of energy being transferred through mechanical work. Later, in the 1840s, James Joule proved this decisively. He built an apparatus where falling weights turned paddles inside a container of water. As the paddles stirred the water's temperature rose. Joule carefully measured how much mechanical work it took to raise the temperature by a specific amount. He found a precise conversion between work and heat. Energy could change forms, but the total remained constant. Heat was not a substance. It was energy itself. From that point on, the caloric theory collapsed, replaced by the modern understanding that heat is energy in motion. But language didn't fully catch up. We still say, "the cold is coming in," or "the cold got me." In reality, what's happening is always the same. Heat is leaving one place and moving to another. Understanding this changes how you interpret everyday experiences. When you step onto a tiled floor and it feels colder than the carpet beside it, the tile isn't actually colder. It's just pulling heat out of your feet faster. When you hold a metal spoon in hot soup and it feels hotter than the soup itself, it's because the metal transfers heat into your skin more efficiently. What you feel as temperature is not temperature itself. It's the rate of heat transfer between your body and the environment. Your nervous system senses energy flow, not absolute energy levels. This also explains something that seems counterintuitive about space. People often say space is extremely cold. In a sense, that's true. A thermometer placed in deep space would eventually read a temperature just a few degrees above absolute zero. But if you were floating there in a proper suit, you wouldn't freeze instantly. In fact, one of the challenges astronauts face is shedding excess heat, not staying warm. That's because in space, there's almost no matter to carry heat away from you. On Earth, cold air removes heat quickly through conduction and convection. In space, heat can only leave your body by radiation, by emitting infrared light. That process is comparatively slow, so space isn't full of cold attacking you. It's simply empty. Your heat drifts away gradually because nothing replaces it. And this brings us to another important idea, one that ties temperature directly to light itself. Because every object with temperature is constantly radiating energy outward into the universe. Every object around you is radiating energy all the time. You, the walls, the chair you're sitting on, everything with temperature emits electromagnetic radiation. At room temperature, this radiation is mostly infrared, invisible to your eyes, but very real. Night vision cameras work by detecting this glow of heat. As objects get hotter, the radiation becomes stronger and shifts toward visible light. Heat a piece of metal, and it first glows dull red, then orange, then yellow, then white. The color itself becomes a thermometer. This constant emission of radiation means objects are always losing energy. If they absorb more radiation than they emit, they warm up. If they emit more than they absorb, they cool down. That's what happens in deep space. In the shade, far from stars, you absorb almost nothing, but still radiate energy outward. Slowly, you cool. Not because cold attacks you, but because your heat is escaping, and nothing replaces it. This principle also explains something puzzling that happens during phase changes, like melting or boiling. Put ice in a warm room and heat flows into it. The ice warms to 0 degrees Celsius, and then something strange occurs. Even though heat keeps entering, the temperature stops rising. The ice begins to melt, but it stays at 0 until every bit has turned to liquid. Where did the energy go? It went into breaking the bonds that hold the ice crystal together. That energy doesn't increase motion immediately. It changes structure. It frees the molecules so they can slide past each other instead of being locked in place. This stored energy is called latent heat. The same thing happens when water boils. At 100 degrees Celsius, the temperature plateaus while heat continues to flow in. That energy separates molecules completely so they can escape as vapor. Steam carries enormous latent heat, which is why steam burns are so severe. When steam condenses on your skin, it releases that stored energy instantly. None of this involves cold entering anything. Whenever water freezes, it's because heat leaves the liquid. As energy escapes, molecules slow enough to lock into a crystal structure. Freezing is not the arrival of cold. It's the departure of heat. Now consider how we actually measure temperature. Traditional thermometers relied on expansion. Mercury rises in a glass tube because its atoms vibrate more vigorously when heated, pushing them farther apart. Modern thermometers use electrical resistance, infrared radiation, or voltage differences between metals. But every method is detecting motion, energy, or radiation. They all measure something real. None of them measure cold because there's no such physical quantity. This understanding isn't just philosophical. It shapes technology everywhere. Every engine, power plant, and cooling system works by moving heat. A car engine burns fuel to release energy as heat. That heat makes gases expand and push pistons, converting thermal energy into motion. But no engine can convert all heat into useful work. Some of it must be dumped into the environment. That's why engines have radiators. They're releasing excess heat so the system can keep running. The efficiency of any engine depends on the temperature difference between its hot and cold parts. The greater the difference, the more work you can extract. This principle was formalized by the physicist Sadi Carnot. He showed that the maximum efficiency depends only on temperatures measured from absolute zero. If the hot reservoir is twice as hot as the cold one in Kelvin, you can at best convert half the heat into useful work. The rest must flow away. Power plants follow exactly the same rule. They create heat, turn water into steam, spin turbines, and generate electricity. But they must release huge amounts of waste heat into rivers or cooling towers. No technology can escape this limit because it's built into the laws of thermodynamics. Understanding that heat is the real quantity and cold merely its absence reveals why the universe behaves the way it does. Processes happen because energy differences exist. Remove those differences, and nothing happens at all. If every part of the universe were the same temperature, no engine could run, no star could shine, and no life could function. And this realization leads us somewhere even deeper, because the spreading of heat isn't just a local effect. It's happening across the entire cosmos, shaping the history and the future of the universe itself. The spreading of heat across the universe isn't just a detail of physics. It tells the story of time itself. Right after the Big Bang, everything was unimaginably hot. Matter and energy were packed tightly together, vibrating with enormous intensity. As the universe expanded, that motion gradually slowed. Energy spread out, temperatures dropped, and structure began to form. Stars, planets, galaxies, and eventually life. The warmth you feel today is, in a very real sense, leftover motion from that ancient beginning. The heat of the sun, the warmth of your body, the energy in your food, all of it traces back to the universe's early heat. And as time moves forward, that energy continues to disperse. Stars burn their fuel, radiation spreads into space, and temperature differences slowly flatten out. Far in the future, trillions of years from now, the universe may reach a state where everything is nearly the same temperature everywhere. No gradients, no flows, no usable energy differences left. This is what physicists call the heat death of the universe. It's not destruction by cold. It's the quiet leveling of energy until nothing drives change anymore. So when you feel a winter chill or step into a cold room, what you're experiencing isn't the arrival of some substance called cold. You're witnessing energy moving, redistributing, balancing itself across the world. Heat is the traveler, always flowing from where it's concentrated to where it's sparse. And once you see temperature this way, everyday experiences look different. A breeze isn't bringing cold, it's carrying your heat away. A freezer isn't creating cold, it's pumping heat elsewhere. The universe itself isn't growing colder, it's simply spreading its energy thinner and thinner across space and time. So here's something to think about. If cold isn't real, if it's only the absence of heat, why do humans treat it as a thing? Maybe it says something about how our minds work, how we turn absences into objects just to make the world easier to understand.